Now let's look at the solution for this very important question, which is rather many times previous entrance examinations question. Here we are given with a solid conductor of considerable radius in the cylindrical form. So it's not a thin conductor, it's of a finite radius is offered. Now as this conductor is carrying current, magnetic field is set both inside the conductor as well as outside the conductor. When we were to calculate the magnetic field induction at a point outside the conductor, it becomes a simple question based on Ampere's law, that is Ampere's circuital law. That is given by a simple formula, mu naught by 4 pi into 2I divided by x, where x is the distance of the point from the axis of the conductor. So that in the other way it implies that for any point outside the conductor, the total current I which is taken along the axis of the conductor is all referred to. But when a point is given within the conductor, here in this case radius is 5 centimeters, distance of the point from the axis is only 4 centimeters. It means the point lies inside the conductor. So when we refer to a point inside the conductor, we have to be cautious with two important modifications. Number one is the permeability of the medium has to be considered. When the point is outside, only permeability of air, that is mu naught, we express. But when we refer to the point inside, permeability of the medium mu comes into our formula. So which is of course we express as mu r into mu naught. And secondly, with respect to the point P now, the current I is all cannot be referred to. The I now is attributed to the total cross section pi r square. When we refer to the point P, we have to consider a circular cross section taking the distance of the point from the axis as radius. So our circular cross section for which we have to take the current is only pi x square. Therefore, in this context the formula is slightly modified, and now let us look at the approach of arriving at the magnetic field induction at the point P. By Ampere's law, Ampere's circuital law, so of course we call simply Ampere's law, B bar magnetic field induction at point P, which is now referred inside the conductor, is equal to mu r mu naught by 4 pi. Actually this is mu, which is permeability of the medium, but when relative permeability is given to us, therefore I am expressing it as mu r into mu naught by 4 pi into 2 I prime. Look at this, I prime I am taking, this is not I, means some other current, now we have to calculate, divided by x, where x is the distance of the point from the axis. Here I prime is equal to, now let us first calculate the current per unit cross-sectional area of the conductor, that is I by pi r square, because I belongs to the total cross-sectional area, uniformly distributed. So per unit cross-sectional area I by pi r square into pi x square, in reference to our cross-sectional area is pi x square. So this is equal to I into x square by r square. So this is a very important or logical conclusion. We can directly make use of this expression. Therefore, I prime in the given context, I is given as 3 amperes, 3 into x is 4 centimeters, so 4 square divided by r is 5 centimeters, 5 square. Both are being in centimeters and we are taking ratio. We need not make any modification of it now into meters, not required. So this is equal to 48 divided by 25 amperes. Therefore, because here we are expressing only magnitude, I am taking only magnitude. That also let me write. Therefore, B bar at B at P. Only magnitude I am writing now. Magnitude only. We are, and of course, if you are to take direction also, obviously we have the Ampere's circuital law procedure. We take now the thumb direction as the direction of current, the wrap of the 4 curled fingers when we take, the tangent gives the direction of B bar. So B at P is now equal to, in this formula let us substitute, mu R is given as 1000 into 4 pi into 10 power minus 7 divided by 4 pi. So let's write completely 4 pi into 10 power minus 7 whole divided by 4 pi. Okay, anyhow 4 pi is getting cancelled, into 2 into I prime value we got as 48 divided by 25 divided by x is 4 centimeters. So 4 into 10 power minus 2 meters, as all are being in SI. And this is equal to 9.6 into 10 power minus 3 Tesla. So the magnitude of the magnetic field induction at the referred point P, which is inside the conductor, is 9.6 into 10 power minus 3 Tesla, and hence option 1 is our correct answer.